Hey folks, so in this video, we're going to start taking a look at the underlying data structure that we're going to use to represent graphs. Obviously, we need some way to store these things before we can actually do cool things like have algorithms that give us interesting results from them. So what is it that we're going to do? Well, we're going to have two different approaches we're going to look at, something called an adjacency list and an adjacency matrix. But before we even talk about those, we need to talk about what we want, right? So what is it that we want from our data structures, right? What are the guidelines for actually implementing this thing? So we have some things we ideally want, right? So the first thing is, right, low space usage, right? So it would be ideal, right, if it didn't take a whole lot of space to store our graphs. And the thing is, right, actually, so there's somehow a trade-off here, right? So we talk about, maybe being, using less space versus being faster, right, or being slower versus using less space, right? There's always this trade-off here, right, between space and time, right? You get, you can try, right, to get the best of both worlds, but it's typically not going to work out for you. Typically, you sacrifice one for the other, okay? So we would want, right, ideally, right, low space usage. Now, when we talk about space usage, we'll actually talk about, well, actually it looks a little bit like a big or a little bit like a tilde. We'll have, for example, this expression here, v plus e, okay? So this is me actually saying, oh, it would be nice if the graph data structure was tilde of v plus e, right? That's what I'm actually saying here. And it's actually legit to do that, right? So we'll use our big O, we'll use our analysis algorithm stuff to talk about at least space usage for this data structure, because it is important to us. And then I have right there on the screen, right, this little exclamation point right over v plus e. So what is that about? Well, that's about the fact that I have two letters there, right? So in the past, we've been looking at things where it's like, well, my analysis is over one thing, right? So it's O of n squared or something like that, right? It's one letter. We no longer have that. We have v and e. Because the problem is the complexity of a graph is highly dependent on the number of edges and vertices, right? So if I have a graph that looks like this, right? Well, it's v equals 6. Versus e equal 0, right? That's one thing. But I could also have this. Let's see, 1, 2, 3, 4, and then I go, okay, so that's v equal 4, and then e equals 6, right? So I can have basically my graphs be vastly different depending on whether there are lots of edges or whether there are lots of nodes, right? And you could even make this worse, right? So it's like I add another node over here, right? All of a sudden it's like, well, I have this connection, this connection, this connection, this, right? I could have all sorts of things right that are happening, and it could be just kind of a complete mess. So it depends, right? Which of those values is large, right? Both of them have significant impact on our algorithms. They have significant impact on our data structures. So we need to keep track of both of them independently. So typically we'll write things in terms of v and e, right? Two different variables. So moving along, some other features we'd like to have is, for example, the fast ability to add edges, right? So I'd like to be able to add a new edge, or an edge between 3 and 4, right? Two different nodes in constant time, right? In O of 1 time. That would be ideal. Don't know if we're going to get there. Another thing would be to check to see whether there's a edge on a vertex, right? So if I want to know maybe is this node 0 connected to this node 15, can I check that very quickly, right? Can I check that very quickly? Hopefully I can do it in linear time, right? Maybe I can do it in constant time. Different things, right? And so we're going to look at two different data structures that implement this thing, and both of them are going to have kind of different approaches, and they're going to get different performance for these different items here, right? So we're going to have to go and talk about them. Now, as we move through these, right, we're going to have some other questions we're going to ask, which are basically about what sort of features are being supported. So, for example, self loops and parallel edges, right? So it's a fair question to ask: does this mechanism to implement a graph ADT, or the graph ADT, does it support self loops, right? Does it support this thing, right? Or does it just fail at it, right? Because they won't all work, right? Same thing for parallel edges, right? Will it support this or will it fail at it, right? So those are two kind of yes or no questions we'll always have to ask. So the two different mechanisms we're going to be looking at are listed here at the bottom: an adjacency matrix and an adjacency list. Typically, lists are what people spend the most time on, but it's important to see matrices as well, just because they give us they give us different performance, right? So there are cases where they would be better. It's just those cases are rather uncommon. So in the next couple of videos, we're going to go into that. We're going to talk about how you'd use a matrix and then a list to represent a graph. So I will see you guys in those videos.